My talk is on heterogeneous graph embedding for malicious Azure sign-in detection. This work is with my co-author, Rachel Allen, who is also attending. The agenda for this talk is as follows. First, I will talk about the challenges of authentication detection and motivation behind this work. Then I will discuss about specific Azure Active Directory authentication logs. Later, I'm going to talk about formulating authentication as a graph problem. And then I will discuss about proposed model and experimental results. Finally, I will conclude my talk with summary of the works. The work on authentication has been widely studied on the literature. These include using heuristic or rule-based approach. This involves writing rules to mitigate the attack. However, rule is to be applied often to capture the latest type of attacks. There are other type of approach which involves using supervised model or applying handcrafted feature extracted from the logs on top of black box machine learning models. With this approach, a massive amount of level data is required, and often feature engineering is required to make the approach works. There are third category which involves graphs, which includes applying graph-based analysis and applying similarity metric on the graph nodes of authentication graphs. But many of them are transactive in nature, which means that whenever there is new unseen nodes, it needs to be retrained again and again. Our work complements this graph approach, which through the application of inductive GNN to our heterogeneous graph embedding. The main motivation behind formulating as a heterogeneous graph embedding seeks the following benefits. First, with GNN, it's able to capture both structural information and feature information of the entities involved. This is because GNN are good at gathering message across neighbors of nodes involved. Second, since users are connected to each other, this enables to capture evolving attacks for a newer type of attacks. This is because the attacker needs to infect majority of the network in order to be hidden from detection. Lastly, formulating as a graph approach enables to rely less on feature engineering tasks due to GNN nature of aggregation and summarization across information network. Our work follows closely on the success of many heterogeneous GNN on cyber applications, such as fraud detection. Next, I will go through how a typical Azure authentication process works and how this can be formulated into heterogeneous graph problem. First, an Azure authentication verifies a user identity to make sure a user has the right access for the registered resource or service are protected through the Azure AD. So whenever a user requests a service from a specific ID or device, Azure AD makes sure the user is allowed to access the request service or not. By this criteria, the Azure AD collects information related to the request and the user identity, such as IP address, location, date, time, and whether the authentication also results on a success or a failure case. For example, a typical Azure logs looks like this, with the user information and application information related info, such as the user name, user ID, user email, we can see from there, and user type. At the same time, there are application-related information such as application name, the ID, and all information related to the application, and location-related information, device-related information in regard to that particular authentication request. Second, if we see into this next dialog, there is a box that tells us whether that authentication ends up on a failure case or a success. This means that for every authentication that ends into a failure, there is a particular reason, such as in this case, error validating credential due to invalid username or a password. So later on, we're gonna use this status level for learning, on our semi-supervised learning. To formulate this as an authentication graph, there are four major entities involved: user node, device node, service node, which refers to the application, example, Office 365 or Teams, and authentication node. The main task here is how do we identify if a given authentication is benign or malicious based on the interconnection it makes. In a typical service request include the following facts. An authentication event happens when a user initiated access request to a service from a given device. So what does this mean is a user can have a multiple edge, which indicates can authenticate multiple times. At the same time, a device can have a multiple edge, which indicates can authenticate multiple times from at a different time period. Similarly, a service can have multiple edge toward authentication, which means that a service can be requested by many type of users or devices either at a different time or the same time. So looking into the graph, authentication graph, we can see that the lighter green, which are the authentication, are distinct, which are a combination of entities connected to them, like the user, device, and service, are not need to be distinct. However, each authentication 1, 2, 3, and 4 are completely independent from each other and also different from each other. To formulate this as a graph structure, we can define the following terminologies. So given graph G with vertex V and edge E, where V are nodes and E are connecting edges here, in our case, the vertex includes user, service, device, and authentication, where the total number of vertices in our graph is equal to the number of total users and number of total devices plus the number of unique service and the number of all authentication. Whereas the feature matrix, which are X, indicates the feature associated with each node. This could be feature related to user, feature related to the device, or feature related to the authentication and service. The goal here is to produce an embedding for the authentication node, as it is the main point of interest for the detection purpose. To tackle this problem, we can rewrite this as a finding embedding of authentication node at time t, given users, devices, service, and other authentication nodes involved in the graph. Since every authentication is unique at a given time t, all time-related features associated with authentication node, example, login time, duration, can be associated to the authentication node. For this task, we test a relational graph neural network model to learn embedding of the authentication node in combining with other heterogeneous entities involved. Then the model is trained as a semi-supervised setting using a semi-supervised level provided in the training set. For this specific model, we use Relational Graph Neural Network, R-GCN, which was proposed on the work of Michael et al. R-GCN generalizes GCN when there are multiple types of relations or entities involved. In a typical GCN, since all nodes are similar, aggregation across nodes is done through message passing of neighboring nodes involved. Usually they are homogeneous nodes. Whereas in R-GCN, each relations are treated separately with different weight vector, which means that same relation share same weight vector. In our case, there are 4 types of entities or 4 types of relations: user, device, service, and authentication. Have separate weight aggregation combined at the end with a target node of authentication for learning. For training purpose, we use 2-layer R-GCN network trained using neighboring sampling approach. Recall that graph convolutional networks are variants of convolutional neural networks, which operate directly on graphs. Unlike CNN, GCN uses irregular structure defined by the nodes and edges of a graph. GCN learns the features by aggregating weight features of neighboring nodes for a specific or a target nodes. For example, in this one, we can see that the node aggregation is done based on nodes of 2 and nodes of 1, which are the nodes associated with node 0. Some of the common application of GCN can be such as node or edge classification, fraud detection, recommendation. For further, we can refer to the original paper of the GCN cited on here. Going further, to evaluate the proposed model, we set up the following experimental dataset from real Azure authentication of 199 selected users for 3 months. We still compromise users for 4-day login events. More than 300,000 number of raw events are extracted from Azure AD with total 60 number of raw features. Our training and testing split looks like this. The dataset is pre-processed with some features omitted and other features aggregated. We'll talk about this in the next slide. In total, we end up with a training set of total of 45,000 events with 83 number of features. This included more than 5,000 negative examples, which are indicated as a status failure. For testing set, we use more than 11,000 events. Out of these, 71 of them are negative examples. At the end, we end up building a graph of 60K nodes and above 275,000 edges. Our feature processing looks like the following. First, we select several features and omitting features that are mostly null or non-unique across the logs. We performed one-hot encoding for the few cardinality categorical feature and omitting those categorical feature with a large number of cardinality. Then feature aggregation is done based on the grouping of service, user, device, and timestamp, and creating aggregated feature of statistical metrics such as sum, unique count, max, etc. For semi-supervision, we use the success and failure level of the training set to learn the embedding of the authentication that could result into either failure case or success due to different reasons. This is later used for malicious detection task. So here is the experimental result of the proposed models. There are three types of models compared. The first task is the ability to identify whether every malicious authentication, whether this can be able to be detected or not. The orange line indicates R-GCN binary model trained on the failure success case, but tested to identify if the malicious event could be under a failure case. The blue line indicates an R-GCN embedding output of authentication fed into isolation forest algorithm, a black box anomaly detection algorithm to produce malicious login with higher score compared to the benign authentication. In this case, the isolation forest doesn't have any information about the semi-supervised training used for outputting the embedding layer. The third one, the red line, indicates a baseline isolation forest algorithm tested to detect malicious authentication on a handcrafted feature without any embedding or GNN approach. The result shows the ease of the R-GCN-based model achieves much better performance compared to the baseline model, which is the isolation forest on the using the handcrafted features. The next, we perform another task, which is ability to detect malicious user on aggregated authentication request. This is basically taking the median of anomaly score of users' activity across all application requested. It's more of a summarized version of the previous experiments. As a more of the case, the analysts are more interested in the user identification than every authentication detected. Again, the R-GCN-based detection has a better performance compared to the R-GCN embedding fed into the isolation forest algorithm. Next, we can take a look into the ranking of anomaly score, into digging much more into the output of the two models. As we can see, of a single day event with a malicious event, the table ranks based on the R-GCN anomaly score. The highest score indicates the most suspicious event. User ID indicates user identification, then service, which is related to the type of service requested, fraud level, which is the true fraud level provided, and status flag is the flag, the flag that's flagged by the Azure AD system. So we can see there are agreements among this, the model score compared to the status flag as well as the fraud level. There are also events where the Azure AD system missed but the model ranked as a top 5 anomalies in the given day. For example, the red shaded line indicates an instance where the Azure AD missed the malicious event, but the proposed model has produced a large score for that, or produced it on the top 5 anomalies of that specific days. In summary, the main takeaway from this talk are: first, formulating authentication as a GNN allows to learn much feature embedding with minimal feature engineering process for a vital downstream task. Second, the benefit of modeling authentication as a target node makes it easier to incorporate the temporal information of authentication, which allows us to avoid depending on much user-related historical information. At the same time, the inactive nature of the modeling makes inference on unseen nodes to be convenient. Third, by modeling as a semi-supervised setting enables us to depend on smaller scale of leverage data. This is much easier compared to relying on a massive amount of leverage data for supervised setting. Finally, the result from the R-GCN binary model has a better performance compared to the baseline isolation forest model trained on handcraft features. This indicates the proposed approach has a promising result on this type of problems. Finally, the code for this experiment, other cybersecurity use case, and our team's idea for future work is completely open source and available on GitHub and on NVIDIA Launchpad, where you can use free short-term lab resource for your own experiments. We'd love to hear from you all on how this approach works on Azure Dataset, and collaborate to build out more cybersecurity and machine learning workflows. Thank you.